Hello and welcome into the second video for lesson 5 for Precalculus 1. We're going to do some examples now of the material we saw in lesson 5. So let me share my document camera here for you guys. All right, so the first problems we're going to look at are the domain problems. And so we want to state the domain in interval notation. And so before I start putting down the problems, let me emphasize again, what are the two things that we're worried about? First, is there a denominator? And second, is there an even root? And so depending on if we answer yes to either of those or both of them, then we have to solve these in different fashion. If I don't have a denominator or I don't have an even root, then I don't have any restrictions with the domain. So the first one, I probably should use like A and B here. So the first problem is 3x over x plus 1. So do I have a denominator? Yes, I do. So when I have a denominator, what's my concern? Well, that cannot be 0. So x plus 1 cannot be 0. If I subtract 1, that gives me x cannot be -1. So in interval notation, it's everything from -infinity to -1. Skip -1 and go up to positive infinity. Second one, and let me just revisit this again. So the 3x in the top has nothing to do with our domain. So it's not an even root. So it can be any number. Any number I plug into x here in the numerator is fine. It's not going to cause any issues. So how about square root of x minus 3? And again, for these, I would recommend hitting pause, try to work it out, resume the video, even double time it through if you want, see if you get the right answer. So, do I have a denominator? No. Do I have an even root? Yes, I do. Square root. So when I have an even root, what do I have to do? I have to set the radicand, which is the piece under the root symbol, greater than or equal to 0. So add 3 to both sides, gives me x is greater than or equal to positive 3. So in interval notation, it's included, so it gets a bracket going up to infinity. What if I have 1 over square root of x minus 3? So do I have a denominator? Yes. Do I have an even root? Yes. So that means what? So because of this even root, it would normally mean x minus 3 is greater than or equal to 0, like we had in problem number 2. But because I have it's in the denominator, it cannot be 0. So therefore, I'm setting this one up strictly as x minus 3 is greater than 0, not greater than or equal. It can't be equal to 0. So I get x is greater than 3, which in interval notation looks similar to number 2, but it's a parenthesis, not a bracket, because I cannot have 3 being the answer. It would give me 0 in the denominator. How about x squared minus 25? So do I have a denominator? No, I do not. Do I have an even root? No, I do not. I have an even exponent, but that's not an even root. So that means what? That means I can have any number that I want, which is all real numbers, which in interval notation is -infinity to positive infinity. And lastly, what if I have square root of x over x minus 7? So do I have a denominator? Yes, I do. Do I have an even root? Yes, I do. So I have to find both domains separately and then find the intersection, the overlap. So first in the numerator, I have this square root. So that means what? X is greater than or equal to 0. Okay, that's fine. Nothing more for me to do there, but now the denominator. So I don't want to have that, just doing these separate. So x minus 7 cannot be 0, so x cannot be, if I add 7 to both sides, positive 7. So now when we have these multiple sets, it's better to draw it on a number line. I have greater than or equal to 0, so that's going to be a closed circle going to infinity. And x can't be 7, so that's an open circle at 7, but everything else is fine. And so my overlap is what? Well, my overlap is everything from 0 to infinity, but not including 7. So 0 is included because it's a closed circle, so it's bracket 0, go up to 7. 7's not include. Whoops, sorry. Let me move the paper up there. Hold on just a second. Sorry about that. So 0 is included up to 7, which is not included, so it gets a parenthesis. Then start at 7 again, go up to positive infinity. So that would be your answer for number 5. All right, so that is our various types of domain problems. Very important. We will see it several times for the remainder of the semester here. So now let's look at some algebra of our rational expressions. So first, let's say we just want to simplify. And I'm given x squared minus x minus 2 over x squared plus 3x plus 2. Well, again, remember our all or nothing. So I can't just cancel out the x squareds. I can't just cancel out the 2's. The only thing I can do here is factor both of these. So the top factors into x plus 1, x minus 2. And the bottom factors into x plus 1 and x plus 2. And now I can cancel this entire x plus 1 with this entire x plus 1, leaving me my final answer of x minus 2 over x plus 2. And that's it. So I can't simplify anymore. I can't cancel the x's or the 2's or nothing. That's it. That's my final answer. What if we want to multiply or divide and then simplify? So for the first one, we have x plus 3 over x plus 2 times x plus 4 over x plus 3. So this one, yeah, it's kind of a very simple example, but I can only, first of all, it has to be multiply if I'm going to be canceling anything. So think of when we were dividing fractions, we had to do what? We had to first keep, change, flip. This one's already multiplied, so if there's anything in the top, I can cancel from the bottom. So the x plus 3's will cancel out. And so just multiply across, you get x plus 4 over x plus 2. So again, that was maybe, hopefully not too simple of an example, but you get the idea. Well, what if we have x squared minus 9 over x squared minus 16 divided by x plus 3 over x plus 4? Well, I can factor this first one because x squared minus 9 is what? It's a difference of squares, x plus 3, x minus 3. And x squared minus 16 is a difference of squares, x plus 4, x minus 4, divided by this guy, x plus 3 over x plus 4. Well, nothing cancels here, and I wouldn't cancel anyways because this is division. So I need to keep the original, or the first term rather, not the original, but keep the first term, change it to multiply, and then flip this guy. Now I can cancel if it's possible. So this x plus 3 cancels with this one. X plus 4 cancels with this one. So I'm just left with x minus 3 over x minus 4. So that's our multiplication and division. If it's multiply, just cancel if we can, and then multiply across. If it's division, we have to first keep, change, flip, then we can cancel if possible. How about addition or subtraction, but this is an addition problem. So what if I have 1 over x plus 2 plus 1 over x minus 2? So again, if you remember from the content video, I explained how that rational expressions follow a lot of the same rules as our regular fractions. And we've seen that here with some of these simplify, multiply, divide. Same with addition. We can use that cross multiply method we learned early on, lesson 1, I believe. And so we do what? We can cross multiply this way, 1 times x minus 2, and then plus cross multiply this way, 1 times x plus 2, all over, and then multiply the bottom, x plus 2, x minus 2. So I'm going to leave this factored. I'm not going to FOIL it out because if anything will cancel in the top, I don't want to have to then do double work and factor it. So in the top, this is what? This is x minus 2 plus x plus 2. So the minus 2 and the plus 2 cancel out. So I'm just left with what? X plus x, which is 2x, all over this product, x plus 2, x minus 2, and that's it. So nothing will cancel here. Even if I FOIL out, I'm not going to get a 2x by itself. So that's where this one ends. There's no more simplification we can do. What if we want to rationalize the denominator? So if I have 1 over 3 plus the square root of 2. So remember for this, okay, what's the process? What do we do? Well, we multiply the top and bottom by the conjugate. So 3 minus root 2. 3 minus root 2. So we get what? In the top, we get 3 minus root 2. And in the bottom, we get what? 3 times 3 is 9. And plus root 2 times negative root 2 is minus 2. So we get 3 minus root 2 over 9 minus 2 is 7. And that's it. I can't simplify this anymore. I can't cancel anything out of all of it. So that's as far as I can go. What if I have 2 over square root of 7 minus square root of 5? Uh-oh, 2 radicals. So what? We're still going to do the same thing, right? So we're going to still multiply by the conjugate, which is now root 7 plus root 5. Root 7 plus root 5. So on the top, I get 2 times root 7 plus root 5. And then the denominator, I get square root of 7 times square root of 7, which is 7. And then square root of 7 times positive root 5 is square root of 35. Negative root 5 times root 7 is minus square root of 35. So as we expect, they cancel out. And then negative root 5 times positive root 5 is minus 5. So the bottom with all these radicals, because it's the conjugate, the radical pieces disappear. So I just get 7 minus 5, which is 2. Again, this is why I don't distribute the 2, because now I can cancel this 2 with that 2, and I just get my final answer of square root of 7 plus square root of 5. All right. And then finally, the last couple problems we want to look at here are our non-linear inequalities. And so that's what? That's when we have an inequality with either a product or a quotient. So solve for x and write your answer in interval notation. So the first one, we have x times x plus 2 is greater than 0. All right, there were like what, those 9 steps, I think it was, for solving these. So the first thing, have to have 0 on one side. We have that. Have to have one term. If it's not already, we're fine there. We just have the one term, the product. Factor it if we need to factor. It is already factored, so there's nothing to do there. So now we do what? Now we set each factor equal to 0. So x is 0, x plus 2 is 0. So I get x is 0, x is negative 2. And these are what? These are called critical points because I'm going to draw a number line and put both of these points on the number line and then pick test points in each of these intervals. So this is negative infinity down here, positive infinity. So let's say negative 10. Let's say negative 1 for this interval. And let's say positive 10 for the last interval. And now check these in the inequality or in our product. So if I do negative 10, I get a negative number here. Negative 10 plus 2 is also a negative number. So negative times negative is positive. And if I have done this right, I know what? This interval should be negative and this one should be positive, but let's double check it. Plug in negative 1. So I get negative in the front. Negative 1 plus 2 is a positive number. Negative times positive is indeed negative. And then if I check positive 10, I get a positive number times a positive number, which is positive. So it works out. My number line is alternating, so I can feel pretty good that I've done this problem right so far. Now, I need to decide which interval am I using for my final answer. Well, I want this entire product to be greater than 0. Anything greater than 0 is what? Is positive. So I want the positive intervals, which are on the end here. So this interval is negative infinity to negative 2. This interval is 0 to infinity. I know the infinities always get the parenthesis, and now I have to check these endpoints if they're valid or not. So if I plug in negative 2 into my original here, negative 2 plus 2 is 0. So this entire left side is 0. Is 0 greater than 0? No, it's not. So negative 2 does not make this true. Therefore, I can't use it. So I have to put a parenthesis telling me don't use that number. Same thing for 0. If I plug 0 in here, this whole thing is 0. 0 is not greater than 0. So it also gets a parenthesis. So it's this set or that set, which we know is our union notation. And so this would be our final answer. Second example, x over x plus 2 is less than or equal to 0. So get 0 on one side, it is. Combine it into one term, it is. Factor it, it is. So again, set these equal to 0. So x is 0, x is negative 2. So it's the same, we're going to get the same number line here, right? So negative 2 and 0. Let's do negative 10, negative 1, positive 10. So if I plug in negative 10, I get a negative in the numerator I get a negative in the denominator, negative and divided by negative is positive. And so I'm going to end up with the same signs as I did before. So -1 is a negative in the numerator, positive in the denominator, that's negative. And +10, I get a positive number over positive, which is positive. But the difference here now is that I want what? I want when this quotient, this ratio is less than or equal to 0. Anything less than 0 is negative. So I want the negative interval, which is right here. And that interval starts at -2 and goes up to 0. And so again, I need to test these points to see if they're included or not. Well, if I plug -2 into here, what happens? I get -2 plus 2 is 0. I cannot have a 0 in the denominator. So that's a parenthesis. How about 0? Well, when I plug 0 in the top, I get 0 divided by 2, which is 0. Is 0 less than or equal to 0? Yes, it is. So therefore, 0 would make this quotient true. So that means it gets included, and therefore it gets a bracket. So the answer to this one would be parentheses -2 to 0 with a bracket. So that's it. That is the sample problems for lesson 5. Good luck, and we'll see you guys in lesson 6.